jump to the last paper in this session. Okay, so let's welcome Huang. Okay, so yeah. So Huang is a graduate student at the School of Computer Science and Engineering, Southeastern University, and his research interests include AI infrastructure and the system of the observability, right? Okay, so.
Good afternoon. I'm Huang from Southeast University, and today I will present FreeProbe, our approach to low overhead runtime observability for high performance user space system. And the key idea is simple: decide whether to sample before paying the interception cost. High-performance systems increasingly move critical work into user space. Examples include DPTK and VPP for networking, SPDK and Redis for storage, and distributed learning systems. And these systems are optimized continuously, and their process depends on runtime metric. Without visibility into the hot phase, we cannot identify the right optimizations. And we use two broad classes of metric, infrastructure metric, such as performance counters and schedule statistics, and they are easy to collect but give only a coarse-grained view. So, and second is the internal metric, such as per function latency and invocation frequency and queuing delay. Review wait time is actually spent. They are much more actionable, but also much harder to expose. There are two common ways to obtain internal metric. Static instrumentation runs inline and is fast, but it requires source change, rebuilding, and substantial energy effort. Prior work needs more than 6,000 lines for an F graph, and our own VPP turning work required about 1,000 lines. Runtime instrumentation is easy to deploy using FreeProbe or BPF time, but the interception pace becomes expensive for microseconds scale functions. Sampling appears to solve the overhead problem, but existing tools sample too late. With FreeProbe, we first trap into the kernel and cross the user kernel boundary with BPF time. We still jump to the user space runtime and preserve the execution context. Only then does the eBPF handler decide whether to keep the event. So sampling means avoid collection work, but not interception work. FreeProbe move the last decisions to the beginning of the trap line. It built on PPF time and freedom, while keeping eBPF as the programmable collection module on a sampling means execution return directly to the application. We avoid context saving and the index jump, and eBPF execution only hits the normal instrumentation pace is preserved. The second design components isolation the sampling counter across threads. There are two implementation details. First, context-free sampling is inserted before context preservation and control transfer. So non-sampled events bypass the expensive path entirely. Second, shared counter will introduce race and sampling BIOS. Conventional TLS lookup through pthread gets specific also add a function call to the hot pace. Instead, FreeProbe store the counters in the probe context, reads the thread identified through the FS register on Linux, and indexes the per thread counter directly. We evaluate the FreeProbe on VVP. Here, the target is IPv6 rewrite, whose baseline execution time is about 1.448 microseconds. The bus show interception times and the line shows throughput drop as the sampling rate increasing. UProbe and the BBF time will pay a large fixed cost because sampling occurs inside the eBPF program. 1% sampling rate, FreeProbe at only 1.83% overhead, and 98.6% below UProbe and 94.68% below BPF time. Next, we fix the sampling rate at 5% and vary the target function duration across 5 VPP nodes. As the function becomes shorter, the fixed interception cost dominates UProbe and BPF time. For the shortest node, IP4 drop, their throughput loss reaches 74 and 40%. FreeProbe limits the loss to about 10% because only sampled events pay for context preservation. This shows that the design remains practical and fine granularity. And finally, we isolate the effects of the faster thread indexing. We compare the FS register designed with a baseline that uses pthread gets specific on VPP IPv6 rewrites, removing the TLS API calls and indexing the per thread counter directly improve performance by 31.03%. Yeah, thank you for your attention. I'm happy to take any question.
So that's for maybe from is there any questions from the audience? Okay. So I have a quick question because in your system it depends on the sampling, right?
Yes, sample.
And in your evaluation, you only evaluate VPP application. My question is if we change the other workload, such as maybe AI training or other more like widely adopted workload, whether the sampling will like introduce some like inaccuracy or like some like wrong like results. Will it happen or not? So do you have any ideas on it?
Thank you for your question. And we we can apply not only the VPP and it's based on the dynamic binary instrumentation. So we can apply it to other like VPP this type user space systems, and yes.
Okay. So can we extend other applications rather than just the VPP family for other system like RDMA? So can your system be compatible with these systems or not?
You means we apply the FreeProbe to like the RDMA or
Can it work?
maybe it's we just use like user space systems. We now apply it for the UVP, but it can change to the other systems. RDMA if the eVPF and can instrumentation to the RDMS, so it can do so. Yes, BPPF and the FreeDA is the dynamic binary instrumentation. Yeah.
Oh, so it's just based on the general technique, right?
Yes. Yeah.
Oh, so
thank you.
So let's speak again. Well, we have limited. Okay. Okay, thank you for your presentation. And I have a question. Can you compare your work with the defect time feature?
Sorry, I can't catch that.
Can you compare your work with defect time in detail?
Oh yeah. We compare our FreeProbe to the BPF time because in the BPF time we execute the sampling. We just put the sample logic to the eBPF program, but in the FreeProbe we put the we move the sampling logic to the trampoline. Yes, just move it to the trampoline. It can avoid the context saving and indirect jump and so.